Hello everyone. I am senior researcher here at DTU Health Tech in the group of Anya Boysen's IDUM Center of Excellence. And I'm also, as a fruitful collaboration with Anya and the rest of the group in IDUM, we managed together with Anya and other people to create a spin-out based on technologies that we developed here in DTU related to Raman spectroscopy and Raman microscopy. So I'm already 3 years as a CEO of Lightnovo APS. It's just based 5 kilometers from here. Yes, and I will try to speak today about Raman spectroscopy and Raman microscopy. Where to start? From my point of view, it's nice to start speaking about some subject in a context of related phenomena. And if you speak about Raman spectroscopy, you may also, in relation to it, always think about fluorescence, infrared absorption, UV visible absorption spectroscopy. And it would be nice for us to know more about our particular point of interest, Raman, via interlinks between very shared things. How to start thinking about that? How these phenomena are connected? You can ask yourself, and I am sure most of you have a very fundamental understanding how they are connected. And what I suggest here, we could try to consider. Since we speak about spectroscopy, we should deal with light-matter interaction. Basically, there is a electromagnetic wave, some spectrum, and electromagnetic radiation is interacting with the matter, which could be basically a few atoms linked one with regard to another with some molecular and maybe even intermolecular bonds if there are many water molecules. And then there are several processes happening. And before starting to think what's actually happening, it would be nice to use quantum mechanics approach where we assume that if there is no electromagnetic wave applied, our molecule, which has valence bonds, for example, between hydrogen and oxygen atoms, would be in a ground state. And then if you apply some light, for example, intense light, in order to excite even electron states, there would be some perturbation to our system, and we would have absorption of light, for example. And depends what type of light we apply, we can trigger different energy levels. For example, our molecule could have vibrational bonds, and they would be highlighted here as vibrational levels. Those levels also exist in electronic excited states. However, even vibrational levels would be split into more tiny structure of rotational levels, which means, for example, normal molecule, it would have several degrees of freedom. You can expect bending vibrations, you can expect stretching vibrations of atoms. However, if it is in gas form, you can also expect rotational degrees of freedom. And that would be corresponding to those levels. I just will move one slide forward. When in the past I did Raman spectroscopy and there is nothing in a sample compartment, you just shine your laser into the air. You would see peaks of air, which would be most likely oxygen and nitrogen molecules. And that's how your spectrum would consist if there is nothing else there. And if you zoom in this area, you would see more tiny peaks. Those are rotational structure of this particular molecules. And which means this tiny splitting does exist in gas form. However, how about light-matter interaction? Here, Jablonski diagram, does everyone aware about this term? Jablonski diagram. So yeah, here we could intuitively illustrate multiple phenomena, and the most straightforward way would be infrared absorption, UV visible absorption, which means that you basically apply some spectrum of electromagnetic radiation to your molecule or your sample, and not everything goes through. At some energetic levels, which correspond to specific colors of your white spectrum, for example, you would get less transmission. And that's absorption spectroscopy. It could be in infrared, in far infrared, in visible light, and UV, and X-ray. We can get absorption everywhere. But it's just one part of the story. After absorption of light, there would be emission or scattering of light as a second act of light-matter interaction, and that typically represented by fluorescence spectroscopy and Raman scattering. The difference between these two phenomena, when you have inelastic scattering, Raman phenomena appear simultaneously when you apply laser light. It happens from the virtual states. And since it comes, for example, if you apply electromagnetic pulse, very short pulse, Raman phenomena will appear and disappear simultaneously together with light duration. But fluorescence, no. Fluorescence will appear at certain time delay. In nanosecond, even microsecond could be range, but typically nanosecond, picosecond range. And efficiency of fluorescence is much higher because it actually comes from the real electronic excited states. Raman is significantly less intensive. Photon flow in Raman spectroscopy would be 100 to 1,000 photons per second. It's very little flow for typical Raman active materials. We already discussed that slide. And if you speak about molecular vibrations, which is the core of molecular spectroscopy, you should understand some very basic simple rules. If you consider water molecule, it could have bending vibrations when you change the angle of the molecular bond and between oxygen and hydrogen atoms. But you can change the distance symmetrically or anti-symmetrically. Another important understanding here, how many vibrations theoretically possible in any type of molecule. That would be highlighted by this simple equation. The K rule here, the more atoms you have in your molecule, the more vibrational bonds would be present. And they also could be simply understood by normal periodic vibrations where you care about the strength of your bond and the mass of your atoms. For example, if we have atoms like metal organic atoms, heavy atoms, they would be, according to this equation, most likely concentrated in low frequency Raman shift. So they are heavy atoms and oscillation frequency would be at lower energy. Which means if you study inorganic chemistry, you should care about low frequency Raman. And if you speak about popular organic molecules, where atoms are not that heavy, they could be mostly distributed in entire Raman shift range and even very high frequency range, more than 4,000 inverse centimeters, or more than 3,000 inverse centimeters. By the way, from the strength of the spring, you could feel another intuitively approach. For example, bending vibration in energy or in the frequency is less than stretching. And the reason why, because it's actually much easier to change the angle of the bond rather than change the distance between atoms. So bending vibrations, they are always less in energy than stretching vibrations for the same type of the bond. Another nice analogy when we speak about molecular vibrations would be, for example, in this room we have light, matter interaction happening in real time. And if you will turn on all the light, including light from the outside, what do you think would be with molecules of water and other gases here in our room? If there is nothing in the visible light, we can trigger only temperature, yes, in the room. And temperature kT in energy scale in the frequency in inverse centimeters would be around 200 inverse centimeters. So the normal heat at 20 degrees of Celsius would give you energy pump only for 200 inverse centimeters, which is far infrared. So all these vibrations would be frozen. If we turn off electromagnetic light in this scale, they do not oscillate at all. There would be only something oscillating here in far infrared, and what is that? If we also look again in the energy scale in inverse centimeters, for example, 50,000, that's UV. You could see near infrared, it's around 10,000 inverse centimeters. And typical molecular vibrations would be in mid-infrared range here, between like hundreds to several thousands. But you will actually trigger only intermolecular bonds with heat in the room. It's water with water when they interact, for example, hydrogen bond. That would be only enough to activate those vibrations. And when we speak about Raman spectroscopy, let's try to think about similarities and differences with other types of spectroscopy, for example, infrared. So as we already discussed, in order to get infrared absorption, you need to apply certain spectrum of energy in infrared range, and just several amounts in the spectral domain will go through with the maximum transmission. But where you have oscillation of water, bending or stretching, there would be absorption. For stretching, vibrations quite high, for example, in water. And that's a typical infrared spectrum of water. But then secondary process happening, Raman scattering. And as you could see, Raman spectrum, in terms of peak positions, they are very similar as infrared. That's why these methods, they are complementary. But you could see they are different by peak ratio. It's because another example here would illustrate actually why. So here I was trying to say that there are similarities. You will see peaks in the same positions. And there is a nice example where you wouldn't see that at all, any similarities in spectra for symmetrical molecules, for example, like CO2. And here, this molecule has, in gas form, it has also 3 degrees of freedom. It could be symmetrical stretching. And imagine you have central atom and 2 shell atoms, and symmetricity is the same. You just change the distance, which means you don't change the dipole moment. It's 0. However, you change polarizability this way. And it's very Raman active vibration. On the other hand, other types of vibrations, they do change dipole moment. And since in order to absorb light, you need to have your own charge, your own dipole. And when you change a molecule like that, your already electron cloud is shifted in one of the directions. It's a charge. And now you can interact with light coming through. Since you can absorb, 2 peaks would absorb light, but the peak which always symmetrical, the type of vibration which is always symmetrical, it wouldn't absorb light. It's completely transparent. for absorption. But in Raman scattering, it's very active. So that's where they indeed complementary. Something you cannot collect with infrared, you can collect with Raman. And in more complex structures, it looks like a symmetrical structure back then, but you could see that selection rules, they do not work that straightforward. You could say predominantly symmetrical type of vibrations, they would contribute mostly in Raman, but vibrations with already present dipole moment would be mostly active in infrared. And thinking like that, infrared spectroscopy is much more powerful tool for... You have a question?
Yes, I think I'm a little confused about the graph up there.
Yes.
So there's a peak in the Raman due to the stretching and the Raman scattering, and there's not a peak at the Raman, the other two places, because...
There is no change in polarizability. It's just change in the dipole moment.
Okay.
And if you try to make an analogy for everything else, all symmetrical vibrations, they wouldn't be active in infrared.
Okay.
But they would be very active in Raman. And mostly all organics has H atoms on a shell, CH vibrations, OH vibrations. They have their own shifted electron cloud density, and they are very active in infrared. That's why infrared spectroscopy is still, until now, much more popular and much more useful to study the chemical composition of organic type of molecules. However, Raman, for the same organic molecules, could be more sensitive for the skeleton of molecule. For example, the polymorphs in organic compounds. Raman tend to be much more sensitive to that than infrared. Infrared could also represent you that structure, but less prominent. So it's interesting to know, to be aware of this when you select which method to choose for particular sample. And another illustration, intuitive example about Raman infrared spectroscopy. When we speak about Raman, remember you could pump with laser, single frequency, and you would have scattering as a Stokes shift or anti-Stokes shift, and you can pump in blue. In infrared, you will get the same peaks, but as absorption. But in Raman, you can get the same peaks pumping anywhere, in X-ray, in infrared even. It would be just shift, Stokes and anti-Stokes. That's a nice thing about Raman spectroscopy. For example, if you need more deeper penetration into the tissue, or you want to avoid some fluorescence. So we discussed a little bit about differences and similarities between Raman and infrared. How about Raman and fluorescence? If you look at the spectra, fluorescence spectra are much broader in spectral shape than Raman of the same compound, and it looks like there is not too many similarities. But if you look at the Jablonski diagram, we could memorize ourselves. We apply laser pump, like single frequency pump, and Raman scattering would happen immediately from the so-called virtual state on vibrational sublevels of our molecular bonds present in the molecule. But fluorescence would come with some delay to the lowest excited electron level, and then emission would happen. With this regard, you could see, regardless where you pump here, or you pump in blue or in red, if you are in this domain, fluorescence would have the same spectrum. It wouldn't shift, but Raman would shift. And how to make conditions where they are similar? We should think more, why is this happening? And this time relaxation and time delay happening due to collisions between molecules. They exchange energy. And in order to avoid that, you can freeze your sample, for example. This is at nitrogen temperature fluorescence spectrum, and that's how fluorescence looks at helium temperatures. You see, it's sharpening. I'm not saying that Raman and fluorescence becomes the same. No, it's still a different phenomena. But if you compare directly Raman and fluorescence peak, it's all the same paper. It's called Spolsky effect. You could see the same vibrations because actually they deal with the same vibrational levels, just from different excited states. Another option to do that is avoid collisions, make gas, and you would avoid collisions or minimize the number of those. And indeed, for example, brom-2 molecular, this would be resonance fluorescence and resonance Raman spectrum. Resonance means that you pump with the laser very close to electronic absorption. And they look very similar. It's another way to get them being very similar. But they are different, and you can use that, which we discussed already, yes, this time delay from the lowest electronic level. For example, if you pump your sample with blue and you have some fluorescence, and you have Stokes and anti-Stokes shift as Raman, then you pump in red, and for example, your electronic absorption was somewhere in blue. Your fluorescence would be less, and even less, but it wouldn't change the spectral position, just intensity. That's a nice thing about fluorescence, and you can use that to split two phenomena. This is a type of experiment which I did maybe around 12 years ago with a tunable laser, and you could see I focused laser on a cover glass, and cover glass in infrared pump has typical fluorescence. This is spectral domain, this is tunability range of the laser, and it's just intensity drift. Intensity becomes less. But when I focus in the same spectral range on organic sample like arginine amino acid, I shift my laser and all Raman peaks, they shift accordingly. But if I have the same arginine on the cover glass, you could see, you could split them, you could separate them, and this method is well known and very well used, for example, as shifted excitation Raman difference spectroscopy, where you could split physically by post-processing two effects, one from another. And that's because fluorescence has no dependency on the laser pump in rough estimation. It's not always the truth, but most likely yes. And typically when you have the real, for example, problems in your lab, you would see this in many cases. You are trying to measure the sample. For example, maybe you also already experienced that with mini Raman, and if your sample is a little bit dark, you wouldn't collect much Raman, you would collect mostly fluorescence. And why is that? If you understand how they related, all of these phenomena, you would think about your molecular absorption. Basically, all samples like this one, they are colored. What does it mean? They absorb light, and they automatically would emit light. So there would be huge fluorescence, and we cannot measure Raman from that sample most likely due to huge fluorescence. But if it's a transparent sample, I will show in a few minutes, there is no problem, because you don't have problem with fluorescence which will overlap your Raman, simply because fluorescence is much stronger than Raman in quantum efficiency. Raman happens from virtual states, fluorescence from real states, electronic states. And then we always, when we think about that, let's just try to summarize what we discussed here. Raman, fluorescence, infrared, UV visible spectroscopy. So Raman and infrared, they are complementary. They have selection rules. If you want to study sample in full, you should apply two methods. And if you have some problems with Raman, you wouldn't have fluorescence problem in infrared. If it is like that, infrared would be more preferable. However, what about fluorescence? In order to understand the origin of fluorescence, you should start with UV visible absorption. And there is interlinks like that as well, because, for example, when we discuss far from resonance Raman, we don't really care about absorption. But if we speak about resonance Raman, which could be enhanced by absorption of light, then there would be connections here as well. So I hope at least it made you a feeling that, how to say, there is nothing specific about Raman. It's all about the same. We just need to understand light-matter interaction to deal with any spectroscopy approach. And according to my plan, I want right now to present you this live demo, measure some samples, and then we will make a coffee break and I will continue with more applications and experimental details of Raman spectroscopy. In order to start with that, I have here software of Mini Raman, and we will try to connect it. Let's say I will use this port. So what is this in my hands? It's something we do in our startup. It's a Raman spectrometer. It's loading now. When it's loaded, you will see a spectrum. What we are going to measure? I have here some very basic samples, like those are LEDs. You shouldn't have much interaction in near infrared. For example, two alcohols, methanol and ethanol, we will try to distinguish. You can measure whatever you want you have here around. That's okay. I have several powders. You can try, and you can try then later afterwards. So it's ready to connect. I press connect, and we can turn on the laser, increasing some power here and there. Yeah, that's okay. That's in milliwatts. We should see something. Let's increase the scale. Oh, we have some peaks. 2 peaks, or even more than 2. Yes. And let's capture it, for example. Out of focus. Let's capture. And I can turn on another laser. And another laser doesn't provide me much of the stock shift because of the settings, but it's not the case here. Let's capture it as well. So let's say this was methanol. I will try to measure ethanol. What would you expect? You could see. In high frequency range, we already see, instead of 2 peaks, 3 peaks. Methanol and ethanol, they differ by, methanol has 1 carbon atom and ethanol has 2, and it has more CH vibrations accordingly. That's why you have 3 peaks here of stretching CH. And this is also, that's OH, which is present partially as water, but also as free OH group. How about in fingerprint range? We have quite significant contribution from outside environment here, but anyway, yeah, you could see that we also have more peaks in high frequency range as well. And of course, it's just 200 milliseconds. We could increase the exposure time to see spectrum better. It's live, yeah. So that's the power of Raman spectroscopy. If you have this spectrum saved, you can then do correlation and identify the chemical composition.